All right, everybody, we got one more related rates problem. This is, I think, from the second review packet you guys got is number 15. Sorry, it's a little crooked, but it works. The radius of a circle is increasing at a constant rate of 0.4 meters per second. What is the rate of increase in the area of the circle at the instant when the circumference of the circle is 25 pi meters? So again, follow our same steps, write down what you know, draw your picture, which you can kind of do this at the same time. Write your equation, take your derivative, and fill in what you know. All right, so let's see what we know. The radius of a circle is increasing at a constant rate. Constant rate, derivative. So what is the derivative? It's the derivative of the radius. So dr dt is 0.4 meters per second. Got that. What is the rate of increase in the area? So again, we're looking for a derivative. We are looking for dA dt. That's our unknown. When the circumference of the circle is 25 pi meters. Okay. All right, so let's take a look at what we have going on here. We got a spiffy-diffy circle. Not too much going on really in our picture, not like the ladder problem. We have a radius, and we know that that radius is increasing. So this is going out, it's getting bigger. All right. So they asked us for dA dt. So that's the equation that we want to focus on. We want to know the area formula for a circle. So the area formula for a circle is, of course, pi r squared. Okay. And that's the derivative I'm going to do. So I'm going to do the derivative of this guy. So we've got dA dt on the left. Pi, remember pi, this is not product rule on the right. Pi is just a number. It's just 3.14. So it's like 2 or 4 or 7. It just carries along like a constant. So to do the derivative of pi r squared is just 2 pi r and then a dr dt. Okay. All right. So let's take a look. I don't know dA dt, which is cool because that's what they asked me for. I got 2 pi. I don't know r, but I do have dr dt. Now you can solve this one a couple different ways. You do have the circumference, right? So you could use the circumference to get r and you're home free. Okay, so if you wanted to do that, circumference is equal to 2 pi r, and you know that that's equal to 25 pi. So 25 pi is equal to 2 pi r. Your pi's are going to cancel out. 25 equals 2 r divided by 2, so r is 25 over 2. You can plug that in for r and you're good to go. Absolutely, no problem if that's the way your brain wants to go. Or you could notice that this is 2 pi r right here, which, I mean, that is the circumference. This is equal to the circumference. And you know the circumference is 25 pi. So you can just, you know, fill in 25 pi right there for a 2 pi r because you know that that's 25 pi. That is the circumference. So you can also go that route. But either way, whichever one floats your boat, you'll get there. So we have 25 pi times 0.04. Okay, so assuming that this is probably a calculator problem because they're not going to usually give you decimals without a calculator, but even if they don't, you can change 0.4 into a fraction. I mean, that's 4 over 10 or 2 over 5. So you get 25 pi times 2 over 5, right? This would be 5. That would be 1. So you're going to wind up with 10 pi. Okay. So you get 10 pi, and then again, units. We got area over time, so area again is in some kind of square units. It looks like we're in meters this time, so square meters per second. And there you go. And you know your area is increasing because your radius is increasing. So there's your other related rates problem that was in your packet. And I'll see you in a few more minutes, and we'll do some optimization problems.